How's my favorite class doing tonight? That's good to see. We got a couple minutes before we officially start. Does anybody have any questions? Quick questions. Okay, I have 6 p.m. Everybody give me a green circle if you can hear me. Okay, Yan Wen, are you there? Okay. Frank, are you there?
Yeah.
Frank, are you there? Okay, when we last left, last episode, we had begun talking about the schematic diagrams for the flip-flops and latches that we had been talking in class about. So let's do just a quick little review to make sure we're on the same page. But I don't have a window open here somewhere. Maybe I do, maybe I don't. Okay, let's assume for a second that I have a schematic diagram that looks like that. What do we know about this particular device? Patricia?
Because there's a triangle symbol, it's edge triggered or flip flop.
Okay, that's one thing. What else?
The D, so it may be like a edge triggered D flip flop.
Okay, well, being a D flip-flop, what's that mean?
Um, you can change the output right away.
Okay, well, let's, Dante, why don't you help her out there?
It only has one input, so the D would go through an inverter to hit for R and S, and then for R, and then S would take the straight away, whatever D's value is straight away without being inverted.
Okay, so what you're saying is that we have D and we have an inverted version of D. We just can't see the inverted version. Is that correct? Or is it missing a pin which says inverted D?
The D would be because when it goes into the D splits and goes into R and S, and R gets flipped, and R leads to Q, and not bar Q is just whatever D's input is, whatever the input of D is.
Okay, well, let's hold that for a few minutes. That's pretty close. Let me grab another one over here. Drop it on the screen. What do we know about this one? Just pop your hand up if you want to talk about it. Scott?
This one is a JK flip-flop with an edge trigger.
And what does all that mean?
Okay, so
If I went to my sister and I said, hey, look what I got here, a JK flip-flop that's edge triggered. She goes, so what?
right, so
Tell me a little bit more.
we've got two inputs here, J and K, and then a clock input, which is the pin with the triangle by it. And what we know about this one is that when J and K are both low, whatever state the flip-flop output is in, Q or not Q, it will stay there. If J is high and K is low, then the output Q will be high and not Q will be low, and vice versa. And then if J and K are both high, then when we receive a clock pulse, then we'll be in so-called toggle mode, and the output will switch back and forth between Q and not Q with every pulse of the clock.
Okay, that's pretty good. Pretty good. Let me stick another one up there. What is this one? Yeah.
That's a T flip flop. It does the same thing as the JK flip flop, but it's just one input instead of two.
Okay, so it can't quite do the same thing because it doesn't have four different ways to describe what to do.
Yeah.
So what is it? What pieces of the JK does it actually do? Your answer is right, by the way. What parts of the JK does it emulate?
I think it emulates the J part, right? The high pass.
Okay, anybody want to help him out? Robert?
So it's either toggling or staying the same.
Right, it's either in no change mode or toggle mode. It doesn't have any other way. The T can be held, and every clock it's got to do something. So it's either if T is low, going to stay the same, or if T is high, it's going to change. Now, in practice, very often you won't find these like this, particularly in this case, the T. Is there any reason why the T won't look like this? Why it might have other signals or fewer signals? Let me give you a clue. It has to do with what state Q is in when you turn it on. We already showed that in many of these latches and flip-flops that they can come up in an unknown state. And so if we turn it on and Q is a 0, how do we know if we want it to stay the same for the next cycle or to toggle for the next cycle? And the answer to that is we don't know. So how can we add something to this to fix that problem? Patricia, what do you think?
You add another button, I guess a clock. Can you?
We have a clock.
Oh, you have a clock. What about the clear preset?
There you go. What we would add, for example, is a clear pin. That way we know when we turn it on, if we assert this signal, that Q will be a 0 and not Q will be a 1. We can then turn this off and then asynchronously or synchronously, this was asynchronous, but then we could synchronously pass T through to Q or invert it, depending on whether you wanted no change or you wanted to have a toggle. So one of the ways to control the initial stage of any type of flip-flop or latch is to give it a clear signal or give it, for example, a set signal. So we might say preset. We also might call that pin just set. Either of these would cause Q probably to be high, depending on how we label the pin. Now, normally, you heard me say these are asynchronous signals. Normally, the ones we're going to draw on the top and the bottom will be async as opposed to synchronous. Synchronous means synchronized with the clock. Asynchronous means it doesn't give one hooey about the clock. These also very often on these chips go in as inverted signals. So if I had this and I was asking you to describe this to me, you would tell me it is a T flip-flop with asynchronous, preset, and clear. And then when I ask you about preset and clear, you would say low level or low going. It would be when the signal goes low that they're asserted. I might also ask you about the outputs, in which case you'd say complementary outputs are available. That implies you have Q and not Q. If we did not have Q but only had not Q, you would specifically state that when describing the chip. Because we always make the assumption there is a Q. This is the optional one. But some chips have the not Q instead of the Q. Now, how would we know if this is a flip-flop or a latch? Put your hand up if you know the answer to that. Let me see some fresh hands up in the air. Frank, what do you think?
I'm thinking a latch is asynchronous and the flip-flop is edge triggered.
That's getting there, almost there. If it has a edge trigger, it will be a flip-flop. If it has a clock, but the clock is not edge triggered, it's a synchronous latch. We can build latches. For example, we can build a JK latch. It has no clock. That's still a latch. It's just not a synchronous latch. It's not synchronized with anything. Now, we had a little issue with this guy and his clock. And the reason is because I told you that unless I tell you otherwise, or if you do a data sheet analysis and find out otherwise, will always use MS flip-flops. MS flip-flops are two-stage flip-flops, and they are always, unless I tell you different or unless you find it in the data sheet, always edge triggered, and the actual transference of data is on the falling edge. So they're always falling edge triggered, not rising edge. Now this picture shows it rising edge. We don't care. We know it's an MS flip-flop. Our rule is that the clock is always going to be a falling edge clock. So they could have drawn it that way. They could have drawn it that way. We wouldn't care. It could be either one, and it's still going to be on the falling edge. Now, what's that really mean? Well, if we take this guy, for example, and we show the clock doing its thing, the result of whatever T is going to make it to Q or not Q on the rising edge. And all of the flip-flops we looked at, if they say rising edge, will be synchronized with the rising edge of a clock. However, these, unless I tell you otherwise, will have used the rising edge to move the data from stage 1 to stage 2, and the output will change on the falling edge. So they're always half a clock behind any other flip-flop, unless you design the clocks to have an inverted clock, which then would move this in line with the other one. So keep that as a little detail that you know and you're not telling anybody, so that you'll know how they work in the wild. But almost 100% of the time, you'll find these are MS two-stage flip-flops. And because they're JK, and because they have two stages, the rising clock, no matter what's shown here, they're either showing you the rising clock or they're showing you the falling clock, and they never tell you which one they're showing you. And since they're the opposites of each other, then you're not going to know whether or not they mean rising or falling edge. We know they mean falling edge if it's a two-stage clock. Now, if they show you this way, where this is J, this is clock, and this is K, it makes it look like a latch. For our purposes, there is no such thing as a JK latch. So this also is a two-stage JK flip-flop where the data is getting moved on the falling edge. Even though it looks like a level clocking and looks like it's a positive edge clock, that means this would mean the same thing as well. So when talking about the clock on a JK flip-flop, it defaults to moving to the second stage, which means changing the output on the falling clock. Anybody have any question about that? Because that's kind of confusing, because they give you all sorts of nice data sheets, and then that one thing is almost always wrong in the data sheet, or it's consistent for a company, but among companies it's different. Okay, assuming that was on a test and you had to describe that flip-flop or latch, what would you say it is? Raise your hand. I spelled clock wrong, but that's okay. No, I didn't. That's okay. It just doesn't look like one. It's a Looks like a T. Says CLK. Sargon, what do you think?
I think it's a flip-flop.
What type?
JK flip-flop.
Yep, it's a JK. It's actually an MSJK flip-flop. What else do we know? Dante?
Would it be a MSJK flip-flop with a clear inverted clear pin?
Okay, it does have an inverted clear, which is asynchronous. Make sure you use the word asynchronous when talking about this. And it has one other thing, which is a missing inverted Q, right? It has Q, but it doesn't have not Q. And it's most common to have both. So you'd mention that in describing it. Does not have an inverted output. Hey, somebody give me a description of this one. Besso?
Is it RES clock trigger flip flop?
Well, I don't think it's a flip-flop. Robert, what do you think?
It's going to be a clocked RS latch.
Okay. And just level clocked.
Right.
Okay. Q normally follows set on the rising clock edge. Is that true? Here's my clock moving along. This is set. This is reset. When we start out, is our clock. Let's assume that Q is equal to a 1. What happens now? Who wants to describe to me what happens? This is S. This is R. This is the clock. Scott, what do you think?
Since this since this circuit is not edge triggered, both of those set and reset inputs will be read whenever the clock is high.
So what that means is the clock will go high
Yeah,
as long as this is inside that edge
right.
when that goes high.
Yeah,
Otherwise-
so Q goes high when set goes high.
Uh-huh.
Then it will
And
go
now
back.
what happens right here? I'm still inside that high clock.
Right, so it'll go back to low here.
Okay.
Then it will stay low. Now, the clock goes high again, but additional resets don't cause any change in the output here. So Q will continue to stay low till we get to that S signal high. Then it'll go back to high. And then the Q will stay high all the way to the end.
All the way to the end. Yes, very good. Very good job describing that. Okay, so that's kind of critical to know how they work with a level clock. Now let's assume for a second that instead of S and R, these are J and K. I'm going to erase Q here. Who wants to walk me through this one like Scott did? We could always let him do it again, and then he'd get all the credit for knowing the stuff, and you guys wouldn't. Okay, there's two events on our JK flip-flop, because remember they have to be MS flip-flops if we're using them. And I don't tell you otherwise. That means on this rising edge right here, we start allowing the data in. But it's only going to go halfway through the chip until the falling edge. So whatever the signals are on the falling edge, which don't change, right? 0, 0, is what actually gets transferred out to Q. So Q stayed the same, and it continues to stay the same. Now we have a rising edge, which is going to allow anything that happens inside of this rising edge to be transferred to the inputs of the second stage. Both of them will have gone away by the time we get to the falling edge. So once again, it's a 0, 0. This continues. So because we didn't plan on when these changes were relative to the edges, we didn't affect the output one bit. Think about that a little bit. Let that sink in. It takes two parts of a clock to transfer things. A rising edge to move it from the input pins halfway through the chip. That's when they're going to grab hold of the data that needs to be transferred to the end of it during the low clock part or the dropped edge part. And some people find that confusing. Let me see if I have the old JK flip-flop laying around here somewhere. Is that one? No. Is that one? Yes. As I said last time, this is old terminology. We don't use it anymore. This is an MS flip-flop. The clock has a high part and a low part. Since we don't have any capacitors or anything in here to grab the edges, what we have to rely on is the edge that occurs between the clock and the inversion of the clock. If I have a clock and it's doing this, the inverted clock is doing that. So at the point where this transitions, we actually transfer from the last S and R stage to the Qs. During the first part, while it's high over here, we're going to transfer from the J and K inputs to the S and Rs. So the clock is low. When it goes high, whatever J and K are, and if they can change, as they change, S and R are changing to reflect whatever they say. However, at the point where this goes low, that forces this guy to go high. And at that exact instance in time, whatever J and K are, it grabs it. And it passes the results of it to this output. That can't change again because it won't see another rising edge. So we take advantage of that one little instant in time when the first stage goes low and the second one goes high. Doesn't matter how long this stays high. The only time we grabbed this data or could change this data was while that guy was high. And since he's low now, he'll never change again until, of course, the next clock. It's very critical you see that. That's important to see how a flip-flop passes data and the optimization here of not having to use the built-in capacitor in order to cause the derived edge. Anybody have any question about that? Okay, before we move ahead, let me go over a little class info here. On the 18th, which I guess is, what, a couple Thursdays from, or Wednesdays from now? No, that'll be on Monday, won't it? Is that next Monday?
Yes.
Okay, so next Monday, we're going to have a practice exam. It's about 5 questions, but it's mostly to test the procedure to make sure you can get it sent, that you don't send it to me 2 days late and think you're going to get a grade, that you can get the correct question. Remember, everybody has to download a separate set of questions, and that you're able to, you know, fill in the blanks within the blanks and not get carried away and do something different. So I guess next Monday, we will take a practice exam, and literally it'll take 10 minutes. It can't take much more than that. The hardest part is understanding what the rules are, but once you understand them once, every time you take a test from me, they'll be the same rules. So on the 21st, that's a Thursday night. Unless something gets in the way, I will probably hold a separate review session that night for anybody that would like to have a review. So if you're interested, give me a little green circle now if you think you're going to be. Yeah, I don't care if I show up and only one person shows up, that's fine. But people in the past have usually found it to be useful when we do a little review, but it's completely optional. If you don't come, it doesn't affect your grade in any way. If you do come, it doesn't affect your grade in any way unless it helps you on the test. So it's not like you're going to get extra credit for coming. It's not like you'll lose points if you don't come. Totally an optional class, and it'll be on a Thursday night about 6 o'clock, whatever time this class starts, I guess 6 o'clock. And we'll talk about the things, well, not talk about the things that are on the exam because I won't have a copy of the exam at that point, but that we'll talk about the things that potentially will be on the exam. The exam itself will be on the 25th. Let me double check that just to make sure I'm looking at the right times and dates here. Yeah, the 25th, which is a Monday night. Last Monday in October. And it'll take the entire class period, and those of you that have accommodations for slightly longer will extend beyond that for whatever amount of time you've been given by the Mercer people. And it's perfectly okay to finish early. Just be very careful on the exam because it's highly likely that if you misread questions or you answer the wrong thing, you'll get the question wrong. And we'll talk about the rules when we do the practice exam about what you can use and what you can't use on the exam. Some things are not allowed. Now, I can't always monitor that, but believe me, I have ways of knowing lots of things that you don't think I know about how you're taking the exam. So just don't test me. Just please don't. Anybody have any questions about that? The material we'll be covering will be whatever was in the syllabus up through that time, which means we will have done in class everything up, including VHDL. We will not have a test over Verilog or VHDL. There may be a few scattered questions about just the architecture in general, but most of it will, if you get up through this Unit 13, you'll be doing fine. Tonight, we're covering counters and shift registers and maybe start finite state machines. And then we'll get some of this loose material that we need in order to, on I guess it'd be the 27th, start designing our first microprocessor, which is the SAP1. And that'll be the Wednesday right after the exam. Anybody have any questions? Stephen?
So for the exam, do we come into the Blackboard Collaborative, or do you just email us and we do it throughout the time of the class?
You'll come to class.
Okay. Great, thanks.
Any other questions? Give me a green circle if you think you're going to do well on the exam. Okay, good. I would expect most of you to do well on it. Some people get surprised because they're counting on doing something which is probably not something they're allowed to do in order to answer the questions. And then when I ask that musical question of show me your work, they get in quite a bit of trouble over that. But in general, if you have done what you're supposed to do by the time you get to the exam, you should be ready to go. And like they say, the review is mostly just to bolster your confidence. It's not to teach you new things. And so it is an optional activity, and you don't have to be here. I don't even write down who's here. So, don't think you're going to get extra credit by showing up or butter me up by being here. I'll do a review if there's one person in the room. And if there's none, I'll probably still do the review just for myself. Okay, let us move ahead. We have talked in the past in some of our diagrams about a box that was called a register. And I didn't really explain it. I just said sometime in the future we'll be talking about registers, and it'll make a little more sense what we were talking about at the time. Let me see if I have any of those nearby. I probably have already put them all up. That one we did that had it. Now this, I did describe A and B's as being in registers. So, and this is the adder subtractor that we were looking at. So what we would think of here is this box. This would be A3, A2, A1, and A0. And the purpose of a register is to hold data until you need it. So let me see, how do I get back from that? There's one. A 4-bit register. And we built ourselves a data selector or a 1 of 10 decoder. So we said this thing is going to somehow hold 4 bits of data. And then we will use our bus architecture here to specifically address that combination and produce an output. And in this case, it produces 0 to 9. So A through F, if they were generated in the register, won't appear because there's no result from that. We could implement one this way, and we might. We also, there's a little bit of fanciness we'll add to it in a couple of lectures. But for now, this is a good enough way to think about it. What type of flip-flops are these? Just raise your hand if you know. Scott, what do you think?
D flip-flops with one output.
Right, they're D outputs with just the positive output. They do not have any presets or clears. We're able to set D to a value, wait for the clock, and then the Q associated with that D will get set. So if I had here 0, 1, 1, 0 coming from somewhere, I don't care where it's coming from, and I wanted to capture it. In this case here, do I wait for the rising or the falling edge? Peter, what do you think? Daniel? Oh, not Daniel, Dante. I don't have a Daniel in here. Numar?
Not too sure, Professor.
Yeah, and when?
I have no idea.
Okay, I guess all you were not here on the last class or the first part of tonight. Very interesting. Mohammed?
Professor, is it rising edge?
Why would it be a rising edge?
Because I mean since it's a D flip flop. I mean when it's because when I'm just looking at the picture and it's like when the current is flowing, because since there is those what is it called? When the signal goes up, I really don't. I'm out of words. I don't know how to explain it. I'm sorry.
Okay.
I just took a guess. I was there.
Anybody else want to take a shot? Robert?
Because it's edge clocked and it's not an MS flip flop.
Right. We got a positive edge clock right there. Right there. There and there. So if we have two edge clocks, we would expect whatever is on D to get transferred to Q on the rising edge. Well, there's the rising edge. When we get to that rising edge, the 0 that's on D gets transferred here. We didn't know what it was. The 1 that's here gets transferred there. The 1 that's here gets transferred there. The 0 that's here gets transferred there. So it's just a simple plain action of a D flip-flop. Now, you don't have to have a repeating clock. It could happen once and never happen again, in which case we latch in whatever we have and just hold on to it forever. But in the case where it changes, the next time X is going to be passed through, or actually D is passed through to Q, is going to happen on the next rising edge, which is right here. So let's assume this guy changed, but nobody else did. Once we get to this rising edge, now we'll get a 0 pushed through to here. How long did we have to hold the signal on X after the rising edge? We know the answer to that. Well, we would have to look at the data sheet for the D flip-flop we're using, and we'd have to get the hold time, because that's the amount of time after a rising edge that a signal needs to be maintained in its present value for the latch to work correctly. When I say latch with a flip-flop, I'm just saying it's done on this edge instead of level triggered. So we have a hold time. How close to the rising edge can I change X and still have it successfully transferred through to Q? Mikhail, what do we call it?
Is it 1 clock cycle?
No. Robert?
It would be the same as the hold time, correct?
Nope. Let's review over here for a second. I have an edge trigger. Let me get a drink of water here. I'll be right back. Oops, I don't want to raise my... There we go. On this edge, because it's not necessarily purely vertical, it has a slight tilt to it. And we don't know exactly where on this edge it's going to grab the data. So once we have the edge, there's an amount of time we need to keep the data signal steady so that we're guaranteed that we will have gotten it. This little piece of time is called the hold time. Prior to that, we need to make sure we have stable data because we don't know where along this line it's going to happen. But in advance of this line, we have to have our data steady. So in case it grabs it low or grabs it high, we'll have it covered. This little chunk of time is called the setup time. And we'd look those up in the data sheet. And they often matter whether the hold time or setup time is going low or going high on the signal itself. Sometimes the setup time for a low going signal is different than for a high going signal. Sometimes the hold is the same. So in our case over here, the time in front of the high going clock is called the setup time. And it has a finite value to it. As a matter of fact, if you add these two times up and you have an alternating clock, they can never get closer together than those two times. So they are part of what causes the maximum frequency. So the maximum frequency, you can vary the signal, meaning turn the clock up and down, requires you have a leading setup time and a following or trailing hold time in order for you to be able to capture it. Clock's too fast, these start to overlap, and you don't get reasonably valid signals. So I wait for the rising clock. I'm going to hold my signal in X steady for setup time in front of the clock, for hold time after the clock. Does Q change instantly? You can give me a green circle or a red box or a red thing if you want to. And if it's not instantly, how long does it take to make its change? Okay, what do we call that time? We had the same thing if we were, just talking about an AND gate or a NAND gate. So if I have one of that, actually, probably can't paste that in, can I? I did over here in the corner. If I change signal A, oops. Where'd my pencil go? There it is. If I change signal A and B in such a way that they're going to cause Y to change, when we're talking pure combinational logic, we said it happens instantly. Well, we also said that in real life, it can't happen instantly. And although this is not a sequential device, A and B changing will cause this to change sometime in the future. What was that time called? What is the time called between the inputs and outputs of any type of gate, or in the case of a flip-flop, between the clock edge and when the actual data changes? Scott?
Propagation delay.
Right, it's the propagation delay. Now, what is the approximate propagation delay between the time D changes and Q changes? What would that delay be called? Scott, what would we call that?
If memory serves me, or the data sheet I'm reading it right, we've got two different ones we're concerned about. There's TPLH and TPHL.
Okay, that's between the propagation delay for going high and going low.
Right.
And you probably have two numbers. Turns out, though, think about it a second. When I change X, which changes D, it could be 3 hours then that changes. It could be 15 seconds. It could be 0.1 seconds. It could be a month. It's totally dependent on when the clock changes, not when this changes. So there is no name for that delay that happens here in terms of a chip. We might have one in a particular architecture. But the real change here happens relative to the edge of the clock. Q will change relative to the rising edge of the clock, in this case, the rising edge, because of the fact that the data passes from D to Q. Now, D being high and D being low may have different times being caused by the clock transferring it, but the actual transfer is not of D or Q. That's not where we're measuring the time, because literally I could set this now and not change Q for a week. I'd wait, and then I'd raise the clock, which would make it change. Okay, so a register simply says, I'm getting data from somewhere that I want to reserve and keep for later. In order to do that, I take that external data, which is hooked to my Ds, and I cause the clock to go high. I can, of course, bring it back to low if I want, but every time it goes high, I will latch something new in if it's changed. Otherwise, I'll just get the current value of whatever it is. Now, a common error is people set up their input like this. They clock it once, which means my data now is in here and it's valid. Then they relax the inputs, meaning they set it all back to 0. And for some reason, I get another clock. That wipes out the data I was remembering. So where is the data? How do I get to the data that I put inside of these flip-flops? If I was drawing a picture of this, here's a box. The box has a clock. Which we know to be edge triggered. It has 4 inputs. The 4 inputs in this picture are labeled D3, D2, D1, and D0. They're hooked to signals externally, which are named X3, X2, X1, and X0. And then I have my 4 outputs, which are the memory of it, so I can see what's in this box if I ever wanted to look. What are these? Where in here am I going to hook up my wires to see the output? Mikhail?
Do you hook them up on Q3, Q2, Q1, and Q0?
You betcha. That's where my outputs live. So my little diagram here says I can, by raising the clock, trap whatever's sitting external to me, and any point in time I want to look at them, I can look at these 4 wires here, which are Q3, Q21, and Q0. And this could be extended to any number of bits I chose. And since it's loaded in a parallel fashion, meaning all of them receive the clock at the same time, then the data becomes good a set amount of time after the clock goes high. Now, if we're using the data, we know the data is no good for some amount of time after the clock went high. That amount of time is basically the same as the hold time because the data may not have been transferred fully yet. So when it goes high, we want to make sure that we look late enough in this period to be able to get a good signal. Now, a common thing to do is, if we have 2 phases of a clock, is to set all of our data and get everything ready at the start of the low clock. Then to retrieve the data halfway through the high clock. Set the data, retrieve the data. So we could, right here, set all the X's to some value. Wait for the clock. We're guaranteed to meet the setup time. Now, we've got to wait hold time. This has to be held, so we don't want to immediately release this. This is still being held all the way through. But we don't want to look at this until propagation delay time has gone by, which is approximately, if we plan our clocks right, going to allow us to look in the middle of the period here, latch it into something. For example, we could assume that the guy looking at him is another latch. So he's going to see the clock, he's going to snag the data, but he has to wait to get the data. So if I were to just put 2 of these in a row, the first one would change on the rising clock, but the second one would not see good data yet if it tried to change on the same rising clock. And we'll work out that problem as a separate exercise. But just be aware if these are chained, we have to allow for all of those delays that can occur to make sure we get a valid amount of data. Now, we probably talked one time just briefly about overclocking a CPU. What you're really doing when you're overclocking it is you're increasing the heat and increasing the switching times, which means these times can get closer together. Propagation delay becomes shorter, which means you can make the clock shorter, so halfway through is closer together. Closer together means the frequency of the execution of things is faster, to some point where you either overheat the processor or you can't get it any shorter because raising the temperature and raising the clock doesn't cause it to happen any sooner. But be aware, this is a way we can save data that happens to be passing by on the X value, as long as it satisfies the requirement that it is in setup time ready before the clock and will maintain the data to at least hold time after the clock. And we can wait until propagation delay time to actually retrieve it. It'll be snagged into these boxes and available for our use. Okay, let's go on to the next thing we want to look at. Actually, before I do, does anybody have any other questions about this? I wasn't getting a lot of good responses out of you. Okay. Oops, that's from last class. Okay, now this is a controlled buffer register. Controlled simply means that we can say when we want the data to be loaded, as long as we also synchronize with an ongoing clock, or doesn't even have to be an ongoing clock. It can be a one-shot clock that actually causes the load to occur. If you look down at the bottom, what are these four things? Robert?
They're clocked D gates. Or sorry, D latches.
Nope. Sargon?
Clock D flip-flops.
Yep, you betcha. And their output is actually Q. You'll notice there's no output that we can grab hold of. Think of this as also having a little stubby wire that we can plug into as well. So what we would look at if we want to know what's inside the flip-flops is we'd look at those four wires. But those wires also are hooked in such a way that they go up to an AND gate. All four of these are identical, so we can look at the one on the right. This AND gate, if it's true, we'll put a 1 on this OR gate, meaning D would become a 1. If Q is a 0, there would be at least one 0 on this AND gate, so it would always produce a 0, meaning that at least from this half, the OR gate is always seeing a 0. Now, alternative to that path, we have X0, X1, X2, and X3. Those are the same X's we saw in the last diagram. They are hooked also to half an AND gate. If they are high, then if the other line is high, a 1 will pass through, meaning the OR gate will see a 1 and D will see a 1. if they receive a 0, this AND can never be true, meaning this OR will only see a 0 from this half. So it looks like Q or X can control what D is going to be next time. Now, the way we do that is we block one of these AND gates with a load signal when we don't want to use that AND portion. So let's assume for a second that load is a 0. That means the AND gate hooked to any of the loads can never be turned on. It doesn't matter what X is. It can't be turned on. However, the inverse of load, which is inverse of load or load bar or not load, will be a 1, which means the other AND gate could potentially be a 1, completely dependent on whether Q is a 1 or not. So what load does, it picks which of these two AND gates is going to be passed to the OR gate, who in turn will pass his output to D. So assuming load is low, that means we're always going to use the left-hand AND gate. And whatever value Q is, it will keep consistently being passed back to D on every rising clock. If, however, load is a 1, then we're not going to see D. Instead, we're going to see X, and load will let X pass through if it's a 1, and we'll block it if X is a 0, of course, because then we'll get a 0 through. And whatever value X is, it will be passed through to D when load is asserted. So it kind of does what we would expect. If we say load, the data comes from the 4 X's on the next rising clock. If we say not load or load inverted or load bar, then that says don't get load from the X's, instead get it from your output. So we're either going to put a new X in or we're going to recycle whatever's on Q, depending on the setting of load. And when is it going to happen? Is it going to happen as soon as I change load? What do you think, Robert?
I think it would happen on the clock cycle. On the rising clock.
That's correct. It will happen on the next rising clock. Again, assuming that you have changed load and changed the X within hold time and setup time of the actual edge. And also the output, we'd have to wait for it to propagate through the chip if we were looking at the output. So again, our rule of kind of changing things so that everything is ready to go at the start of a cycle. You know, we would change everything, all the whole loads, any of the X's would be changed right here, and holding them completely through the entire clock cycle. And then taking after the clock edge and waiting until the center of that right risen part to look at our output. We should satisfy all of our time delay elements. Remember, this is going to be done at an instant in time. The other one's going to be held for an entire period. So this is probably some rising edge of some clock somewhere that we've synchronized with our clock to be halfway through the clock period. Or we simply arrange that everything doesn't have a long enough hold time for it to matter. There's other ways we could manipulate the clocks. So this is a fairly powerful circuit that we would need, and we'll probably see it again in the future. Notice that load causes all of the X's to be loaded simultaneously. And if we say not load, it causes all of the data to be recycled on every clock. Again, this wouldn't have to be a constantly changing clock. It could have one time in the future when it changes and never change again. And that's the point in time when X would be passed through, Q would become stable and not have to be recycled because we have no more rising clocks. There's one other clock signal we didn't talk about. This is not only a D flip-flop. This has a asynchronous clear. What does that mean when I say asynchronous clear? Scott?
Its effect on the circuit is not connected to the clock signal.
Okay, when does it happen?
It'll be processed more or less right away, or subject
That's
to
right.
delays.
That's right. It still has giving delays that might occur, but we think of it as being completely associated with the or dissociated with the other clock because we want it to happen right now. What value will it set all of the D's to if I do that? Who wants to answer that one? What if I assert clear, don't need the clock, but when I assert clear, what value will all the D's go to? Date?
Would it be 0?
Well, that's a possible answer.
Actually, oh no, would it be whatever default value it's set to?
Well, think about the problem here. If clear happens, what we're really doing is we're clearing Q. So if we're looking at Q right now, which means that load is not asserted, then this will pass through to D, and D will be 0. If, however, load is high, Q doesn't pass through, D just continues maintaining whatever value it had last, because we don't know what the clock is doing, so it's not going to pass a new version of X into D. It'll just keep whatever D had previously. If we do get a rising edge, of course, it'll change to whatever X is. Clear affects the Q output. And as long as we hold this at 0, I'm sorry, we didn't show it on this picture. So as long as we hold this at 1, it doesn't matter what the clock is doing. Q will stay at clear. More than likely in real life, though, this signal is hooked to inverters here, inverter things, which mean when clear is made low, that's when clear happens asynchronously. Normally for asynchronous signals, they'll use the inverse as opposed to the positive going signal. Any other questions about this one? Okay, let us move ahead. I don't think you all are having as much fun as me. I enjoy these things. We'll look at the top part, then the bottom part. This is called a ripple counter. First of all, what type of flip-flops do we have? Put your paw up if you know. Patricia, what do we have?
Edge triggered JK flip flop.
Yeah, we just have some MSJK flip-flops. We see here that they're telling us it's edge triggered and that it's inverted. But for our purposes, we know that means the rising edge is going to latch it from the first stage into the second stage, and this is going to latch it into the output. So we'll see a falling edge is where we're actually going to see Q make its changes. We have an asynchronous clear. We have a signal called high, which is tied to J and K in every chip. Now, our outputs are taken at Q0, Q1, Q2, and Q3. What does a JK flip-flop do when both J and K are a 1? Tamulin?
They are in toggle mode.
That's right. Very good. Yeah, they toggle, meaning that on every tick of the clock, we're going to get Q changing from whatever it used to be. Now, I want you to look at the picture very carefully and tell me, where is the clock hooked? This is the clock over here. It's only hooked to flip-flop Q0. Where is Q1's clock hooked? Where is his clock hooked up? Dante?
Would it be Q1's clock would also be hooked up to?
Or where's his clock go?
Oh, it goes to Q0.
Where's this guy go?
Q1.
This guy.
Q2. So all the
So
clocks are
each
hooked up to
each one is clocking the next one, except for the first one. So if we look at the picture down there, what we'll see is if we provide a clock, low, high, low, high, low, high, to the very first clock on the Q0 chip, every time we get a falling edge, its Q will change. But since we get a falling edge half as often as we get an edge, if this guy is happening 10 times a second, he's only going to happen 5 times a second. And we kind of use powers of 2 here because notice his output is the clock to the next guy. Every time we get a falling edge, the next guy changes. The next guy changes on every falling edge of the preceding stage. Can we get down to the bottom? And he changes every falling edge. Here's a falling edge, so he changed. Now, if we were to look at this for a second, and we just wrote in some numbers here, we call this 0, 0, 0, 0. This guy would be 0, 0, 0, 1. He'd be 0, 0, 1, 0. 0, 0, 1, 1. Anybody see a pattern going on here? Give me a green circle if you see a pattern. And put your hand up if you want to tell me what that pattern is. Mohammed, what is it?
Professor, is it like 2 to the power x? So whatever it is. So if x is 0, it's 1, 0, and then 1, and then 0, and 1. And if x is 2 is 1, 2 to the power 1 is 2 zeros, and 2 ones, and 4 zeros, 4
Okay.
ones.
Okay, anybody else want to elaborate on that? Scott, what do you think?
I look at it as it's counting in binary from 0 upwards, just counting integers.
So if that was the case, we would eventually, this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. We'd be at 14 here. I don't know if there's any more. Now that's about as far as I can scroll to the right. But 15 and 16 would be there. And then on 16, they would all be having a high clock at the same time. As a matter of fact, if we included this original clock, we actually could count to 32. Could you think 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1? We'd have 5 bits of precision. So a ripple counter, this guy right here, is able to count in binary for us. If we ever need numbers which go in an ascending way or even descending, we could wire it so it went the other direction. But we could use a ripple counter. Now, let's put our computer scientist hats on for a second here. What's a disadvantage of a ripple counter? Because it's going to count perfectly from 0 up to, let's say I had 64 bits. It would count all the way up for me, and I would get every combination of zeros and 1 in binary counting order. Scott, what do you think?
Well, to count up to n, whatever it is, it takes n ticks of the clock. You can imagine, I don't know, kind of like doing this ahead of time in some way in one shot, but that's not an option with this approach.
Right. Well, no, this again is like in computer science. If we were talking about, if you wanted to show all the pictures in your album, you've got to show it all the pictures in your album at some point. So if we want to count all the numbers between some number of bits, we actually have to do it. But you're on to one thing about efficiency here. Remember, there's a propagation delay associated with every time we change the output after a clock. And since the clock of this stage is the input to this stage, there's a delay between the time we see a clock and he sees a clock. And then we delay again before he sees it, and delay again before he sees it. So it could take a long time for all the zeros and ones to propagate their way down the clock chain, meaning the actual output of this clock or this counter would be very slow if we had lots of bits and the flip-flops themselves were not fast. However, for short sequences, this is ideal. There's a couple other things that it does very, very well. And I don't know if I have a picture of that or not, but I think I'm going to explain it to you anyway. Let me get a fresh little piece of stuff here. Let's take the output of a 555 timer. And let's assume that I have it set up so that I have a long duty cycle. It's going to be high for a long time and then low. High for a long time and then low. Let's do this a few more cycles here for me. Now let's assume for a second that what I would really like to have is I would like to have a 1 kilohertz That's 1,000 times a second clock for my system. But I want it to have a 50% duty cycle. Meaning I want it to be as high as often as it's low. 555, we know that can't happen because when we charge the capacitor, we're charging through two resistors, which are resistor A and resistor B. And when we discharge the capacitor, we're discharging only through one. So by necessity, the high value will be longer than the low value at its output. But think for a second, what if I took the output of a 555 and I made it the clock to a JK flip-flop? So that every time the clock goes low, I'm going to switch states. Now, this had probably something like a 90% duty cycle. I'm going to run this at 2K hertz. Since this is going to be only happening half as often, this will be running at 1K hertz. But notice what I got for free? I got a 50% duty cycle out of it. So this very irregular thing, as long as I run it twice as fast and run it as the input to my JK flip-flop, I'm going to be able to generate a clock which is 50% at half the frequency. Our SAP1 computer is going to take, in fact, this very circuit we have here and use it to make a regular clock to be used. And again, because we want to set up data here and hold it that long, and we actually want to make changes theoretically in the middle, but we'll design it so that it'll work very close to this edge. We want to actually latch in new data. The more time we have for that propagation delay to occur, the better off we are at getting good data. If we use this, we'd have such a short low time and long high time that we'd have an unreliable clock. But it's perfectly good to use this unreliable clock to generate a very stable clock at a known frequency that we would like. Again, this is one at 50% rather than 90%. Everybody see how that works? Give me a green circle if that kind of makes sense. Now, this clock we'd want to run forever, right? We might block it when we wanted to pause the computer, but in general, we want this to be a constant tick-tock, tick-tock, tick-tock. But clocks don't have to be that way. Over here, when we saw this, we're going to probably create our binary numbers every time we see a thing. But what if we didn't? What if we only wanted to every 5 or every 6 clocks cause this to count up 1? What if we didn't want to do it on every clock, but we wanted to do it? That means we'd have to block some of the clocks that we have, or we'd have to come up with some way to tell this when to count. So what could I hook to this to make it only count on certain ticks? Isn't the real problem that J and K hooked to high mean count every time you see a clock? Isn't that the real problem? What do you think, Mikhail?
So would hooking it to a latch cause any, like, since the latch, the D could hold the input value, so would that be able to change it?
Well, we might be able to use something that's going to be hooked in a different way, different fashion like that. Let's take a look at a diagram that might do that and then think about what the difference is. This will look a little more complicated, I suspect, but not really. There seems to be less things hooked up to this. What's different about this picture and the other picture? There's only one thing really different. See if I still have the other one up here. There's the old one. Doesn't have a clear, but we don't really care about that. There's the old one. There's the new one. Old one, new one. What's the difference there? I don't see any new hands. Patricia.
Instead of a high, it's connected to a count.
Right. Instead of hardwiring this to a 1, we'll hardwire it to a signal that we can change. When it says count, we'll honor the next edge. When it doesn't say count, we won't honor the next edge. And remember, we're using falling edges because these are JK flip-flops. So under our control, meaning if we can control when count is asserted, then we can control when the count goes up in this counter here. That sounds like that could be useful. One of the things this could be useful for is in a microprocessor, there's something called a program counter. The program counter always points at whatever address is in here, whatever number's in here, points at the next instruction to be executed. 0 would be, it would execute the first instruction. A 1 would execute the second instruction. That sort of thing. But what if, in order to execute instruction, it took you 4 steps? You certainly wouldn't want this to advance to the number 4 while you're executing the first instruction. You'd want it to only advance once inside of all 4 of those counts. So you'd have to write some logic somewhere that knew, for example, maybe when I'm in state 2, I need to raise the count signal because that's the state I want on the next falling clock to have the count passed in. So we'll talk about this much later, but it sounds like controlling when this changes the count is usually a good thing, but not always. Sometimes we just want it purely to keep changing, like the main clock of a system. But there could be other times when we want to maintain very, very careful control about what the clock is doing. Anybody have any questions about this? This is actually important. Okay. Another useful one is a type of counter that we'll definitely make use of inside of our CPU, but it's called a ring counter. Take a look at that one and kind of jot down on a little piece of paper what you think the values of it are going to be. Is it going to start with 4 zeros and then go to 0001? Is it going to count in gray code? Is it going to count some other way? Look at that one and see if you can kind of figure out what it does on your own. And once you figure it out, give me a green circle. First of all, ask yourself, what type of flip-flops are you using? And the answer will come back as a D flip-flop. The output from this is going to be taken right here, 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 and here. And we'll give them the name Q0, Q1, Q2, and Q3. So initially, what's going to happen when clear is brought to a 0? What's going to be the value we see at each of the Qs? Okay, well, let's take a stepwise approach to it. Scott, what value will this flip-flop have in it on when we assert clear?
It will be 0, because if clear is 0, then not clear, which
Okay,
is
so
on
this is 0. This is 0. So this says, in order for it to be clear, lower the clear signal. Okay, so this is not clear right now, meaning it's going to give you the correct thing when you assert it. So when we put in the value and clear is asserted, we get a 0 inside of the chip. This one, however, notice is hooked to preset. So Mohammed, what value is going to be inside that particular chip?
It will be 1.
Yeah. So when we say clear to a ring counter, it doesn't set it to all zeros. Sets all of the leading ones to 0 and the last one on the right to a 1. Now we release clear, goes away. We're a D flip-flop, so on every rising edge, something is going to happen. Notice that the rising edge is hooked to all of them being clocked at the same time. So the question is, on the very first rising clock, what gets moved where? Give me a green circle if you know. Okay, well, look at each one. Where is Q0 attached? It's attached to the data of the second one. So if we started out like this, that means the one that's in here is going to be moved here. But at the same time, before that happens, the edge will occur. The 0 that's here gets moved here. The 0 that's here gets moved there. And the 0 that was here gets moved all the way back over to here. We see another rising edge. Everybody moves one left. So it's going to have a 0 here, a 1 here, a 0 here, a 0 there. So if we were to look at the sequence, we see 0, 0, 0, 1, 0, 0, 1, 0, 0, 1, 0, 0, 1, 0, 0, 0, 0, 0, 0, 1. So we've got 4 different ways the number can look, but only 4. Every bit has the ability to be a 0 or a 1, but if you're a 1, you're the only guy. You're an exclusive. A ring counter is another way to count. If we ever find 2 1s turned on, we know there's been an error. If we ever find all zeros, we know there's been an error. So we would do whatever this thing is. Now picture this as repeating forever, because the clock might repeat forever. You know, lay down the bread in that step. Put on the butter. Close the sandwich. Eat the sandwich. Lay down the bread. Put on the butter. Close the sandwich. Eat the sandwich. We could consist of these as being something that indicates to us a unique thing that should be going on now. It gives us a clue that we're in this particular, we'll call it, the word we use later is state. So I might as well use it. You're all big people. What state are we currently in? Are we in the state where we're eating the sandwich? Well, that was the state over here of 1000. And if we were in 0010, we know the sandwich is not being eaten. So we could indicate a particular state by using a ring counter. Now the ring counter needs special startup code on it, right? It needs clear and a set. One of them has to be set, because if we don't set 1 to a 1, then we have all zeros. We'll never get a 1 because we just keep passing zeros around. As long as we only have a 1, 1, a single 1, it'll always get passed as a single 1 unless there's an error. These are sometimes called one-hots. Anybody want to take a guess as to why they're called one-hots? Come on, one of you non-participants, put your hand up. I want to give you at least a the NP. All these people are participants so far. Okay, Jay, why would they call this a one-hot?
I'm not sure, Professor.
There's a wrong answer. Yazoo?
Because only one of those is turned on.
Absolutely. Why didn't you have your hand up? You knew the answer to that. Okay. So yes, we have one item on and always on. So to remind us, I'm calling it a one-hot means it's a type of counter that will always have one thing done. Now you could use this for all sorts of stuff indicating different states, and we'll see reasons why sometimes a one-hot encoding is a good way to encode things. On the other hand, this also can get kind of long. If you were going to count to the number 32, where this meant 1, that meant 2, this meant 3, this meant 4, you'd have to have 32 flip-flops. But the error checking would be rather robust, because if one of them was on, you'd know that was the count, because nobody else would be turned on. Okay, let us move ahead. Had a student, just bad joke coming up. Had a student several semesters ago, and this is actually a true story, who made one of these, he said. But in fact, what he made was a box to put rings in. He hadn't seen this, and when he just saw the slide coming up, he jumped on real quick and said, I made one of those once. And apparently he had his graduation ring and his girlfriend's, engagement ring or something like that in a little box that he called his ring counter. So he took a picture of it and we posted it on the website for that semester. It was quite an interesting thing. He was a little embarrassed, but once he figured out that nobody was really laughing at him, they were just laughing at the situation. It turned out pretty good for him. Okay, now hopefully all of you know this is not for counting finger rings or bathtub rings. Okay, keeping that sort of a let's move things from one box to the other in mind, this is called a shift left register. It's not unlike the ring counter, except we don't have the loop at the end that attaches back to the beginning. The idea behind this is I have some stages where we can pull the output off. Output we come out right where I'm marking it here. But I have a single input. What I want to do is I want to pass that data through into these boxes so that I can take them out in order, but I don't necessarily at this point in time have a reason to give you all of the data. So let's take, for example, I wanted to pass in the number 0101. I would first put a 0 here. On the clock, I would get a 0 here. Now we have no idea what's in these boxes. Now, he has been put into the shift register. Now I'm going to be presenting a 1. So the 1 is going to wind up here. The 0 will move over here. Whatever was here will move, but we don't know what they are yet. I have another 0. This becomes a 0. This 1 got passed over. The 0 came in here. And then finally, I pass in the last 1. So he'll be here. And when I'm all done, this is going to have a 0. He'll have a 1. He'll have a 0. And he'll have a 1. And you kind of go and think about it. What's going to happen next? Well, the next thing that's going to happen is this guy's going to pop out the end. Then this guy will pop out the end. Then he'll pop out, and he'll pop out. And while that doesn't sound particularly interesting in terms of the application we have here, one of the things that we could do with this is we could take something that we had all at once and serialize it so that once everything's here, it could be retaken out once this is full as the serialized number, which would come from those 4 buckets here. Another thing we could do is, for example, let's say that we ran a car wash. Let me find my little thing here. And the car wash is going to have 4 stages to it. First of all, we're going to have a rinse stage. We're going to have a wash stage. We'll have a wax stage. And we'll have a dry stage. Now, our first car comes along, and he paid for a wax. So what we really want to do is we want to pass into this shift register that sits over here the numbers that say he's going to get a rinse, a wash, a wax, and a dry. And then we want to start shifting these in as he moves. So here he is. The first guy which says he got a rinse goes in. Or we could implement it so that all 4 numbers go in advance. Or we could say that we want this to represent where the car is currently in the car wash. So there's a lot of uses we could have for shifting in data based on where this car is. Now that becomes more compounded if we have two cars in the car wash. This guy did not pay for a wax, but he did. So when we get to the wax station, we want to be able to consult the one that's passing through matching what he's doing and see that he had a 0 there. But when this car got to that spot, we'll see that we saved a 1 there. So having some sort of a way of maintaining a state of where we are is often helpful. Another thing we could do is, what is the ASCII character for a capital A? Who can tell me what that is, the 7 bits for that? Capital ASCII A. Stephen?
Is it a 41? Is that it?
Okay, so that's an uppercase A, which we know to be like this. And we also know that this number right here is actually a computed number, computed based on what the other 7 digits are. We had a circuit that did that, computed odd parity for us, for example. In this case, because we need odd parity, this would be a 1. Now, when we transmit data, we transmit it in reverse order, meaning this bit goes first, then this bit, then this bit, then this bit. So a likely way to do that would be to load this into a shift register. So we pick this up. We don't have a picture of one yet, but it's something like a controlled shift register where we just put them all in at once. Assuming we don't have that, we could use the left shift register. This would go in first, followed by the 5 zeros, followed by the 1, followed by the parity bit. So we'd load up the 8 bits in the shift register. In this case, it's an 8-bit shift register. Now we would continue clocking it 8 more times. This would come out, that would come out, that way. And meanwhile, we might be pulling in the next character. But as I did that, I would be getting my characters, including the parity bit, in reverse order and able to send them. In this case, I could pull in the characters, 4 of them, and then I could start taking them out one at a time. I also, in the case of this, have parallel access to whatever character's in here, but I don't have parallel ability to put them in, which if we were building one, we'd probably actually design it that way. Now, we also could simply wire this differently and get it arranged like this. This is a shift right instead of left. Does logically what the other one did, except for where we're putting the clock, same place, but data goes in over on the leftmost position and then gets passed to the one on this side of it. So the thing looks like it's moving the data this direction. Since we're taking the data out right here, of course, we could look at it again internally at each of those spots, but we're literally taking it out here. That's on the opposite end to where we were. Oops, I didn't bring that one down, did I? I must have closed it. To this guy, where we're taking the data out on the left-hand end. Both are useful. It depends on logically which way we want to think about the data moving through the thing. And again, we'll look later at the car wash example and things like that to see how you really would use them as opposed to just saying it could be done. Okay, any question about shift right or shift left? In general, the way these have been drawn, we should be thinking about putting them in 1 bit at a time and taking them out 1 bit at a time. We're basically buffering them the number of stages that are in the shift register. So if we put 4 in, we fill up the shift register. Now it's time to start taking things out. If we continue putting data in, every 4 we will have gotten a new character. But this 4 could have been a big number like a 32, could be a small number like 2. And it basically serves the same purpose that a buffer would in software programming. We're buffering the 1 byte we care about or bit we care about until we need to use it. Now we can fancy this up a little bit by taking the control that we had on the buffer earlier, remember our controlled buffer, and applying it here. Now this shift register, if you look at it carefully, shifts left or shifts right. Give me a green circle if you think it shifts left and a red circle if you think it shifts right. Okay, well, if we look at the buffered part, the controlled part, we're getting data from one of 2 places. The 2 places are controlled by this signal, which is called SHL. What do you think that stands for? Who knows what that stands for? Scott?
I'm going to guess it stands for shift left.
Yeah, shift left. So that's our clue that we're going to be shifting left. And what it's going to do is it has itself and it has an inversion which picks up either one of these 2 AND gates. So either the one on the right or the one on the left is enabled, only one of them. If the one on the left is enabled, we simply recycle the last Q. If, however, the one on the right is enabled, D will be able to be entered and each one gets passed on to the next guy. You notice it comes out of Q and goes to the next guy. Comes out of Q and goes to the next guy. Shift left now says we're able to ignore any clock that we don't want something re-entered because it's only when we re-enter it that it allows a shift to occur. If we're just recycling it, nothing new happens. The old data stays in the bucket. So this is a fairly good shift register. We can take 1 bit in at the DN. Of course, we could look at it by looking at Q, but in general, we'll take 1 D in at DN. It's full, and we take it out at Q3. Although they didn't show that, that's where we would normally take data. And again, we can shift up to 4 stages and buffer it before we start seeing the first thing we shifted in. Every clock will be honored in the sense that it will bring in the next byte or next bit of data. The difference is that we're only bringing in new data if shift left is asserted, and we're just recycling our old data otherwise. Notice the data coming out of us goes either back into the recycle or becomes the new data of the next stage, and it is controlled by shift left. Anybody have any question about this particular diagram? Okay, now there's one more diagram, I think, among these that we're going to look at tonight, which is this one. I don't know if I can get it all on there once. No. Yeah. Now this one has one additional feature to it. It's basically the same as the last one, except now we have 3 AND gates being distinguished. We also added back a clear. The difference here is we can have data passed down the shift register. That would be through DN or through the Q outs, which go to the rightmost AND gate. And of course, data would be taken out serially right here. Additionally to that, we have a shift left signal. Notice that shift left is asserted as the controlling signal for the rightmost AND gate, which is the one that lets DN come in. And it's also being used as part of this NAND gate here, or NOR gate, I'm sorry, it's a NOR gate, which is controlling whether or not this gate or that gate is the other one being used. Because load needs to control the center gate, but what we call broadside LAN is going to control the broadside load. But what we're considering to be the recycling AND gate, the one that picks up Q0 this direction, has to be guaranteed not to be turned on if load and shift left are turned on. If you look at just the logic here of the machine, you'll see that that's the case. So the way this works is we can not assert this, not assert that, and it will ignore DN. Instead, it will continuously recycle Q0, Q1, Q2, and Q3 through the backwards path. So if you go up, it'll be back to the same side, back to the same one. If, however, shift left is asserted, then all of the gates will pass whatever's in them to the guy to their left, except the last guy will pass it out and drop it on the floor unless we use it. If, however, both of those are zeros and load is asserted, we will take the X's and immediately put them into these flip-flops. So we don't have to DN pass them down 4 states, just whatever's here. And this is called a broadside load because we're bringing it in the side of the shift register. We're putting the entire thing in at once. We're probably going to undo load then, and we'll shift out the data that's in it right now. We won't worry about loading new stuff serially because we were able to put it in broadside. We still could bring it in serially, but we may not. So this is about the most potent of the shift registers that we're going to be looking at. Anybody have any questions about this one? Okay, well, all of these gates are very important that we have. I'm going to, actually, I wasn't going to, but I'm going to give you a copy of them so that you have them in your notes. Let me see if I can figure out what the name of the file is. Okay, let me get a copy of the website here. I think what it's called is let me try it once and see if that's it. Apparently not. Oh, I didn't put a slash in there. Do it again. Should be a /. Yeah. So that's its name. So get that downloaded. Let me know you got it. Okay, that's not what I wanted. I do want the 555 timer, but not that particular picture. I'll grab that one as well. Did we have the data sheet for that? I don't have a little thing at the top up here anymore for it, so I must have put it in my bookmarks somewhere. Okay, in here, if we go back just a ways, I think on page 11, if I'm in the same data sheet. Yeah, we have the astable operation of this chip. Now, what I was telling you earlier about using this as the clock for our first processor that we designed, one of the things we'd have to be concerned about is no longer the duty cycle of the thing, because as we looked at it, where is it here? We said that the thing could have a really cockeyed duty cycle like this. And if we had this driving D flip-flops, for example. So this is the 555 up here. And we only changed on the falling edges. We might design it to change on the rising edges, but the key thing to notice about this is, first of all, we know that is the period of one clock cycle on the 555. On our flip-flop, we know it's this. Notice this is twice as long as that. My picture is not very good, but it's twice as long. So this is the period, meaning in seconds. If we put 1 over the period, we're going to be equal to frequency in hertz. Well, this guy takes a longer period, so inverting him is going to give us a slower frequency, a lower number. And I just kind of said, okay, this guy's going to be 2K, and this is going to be 1K. Let's assume we wanted to actually design that. And what we were trying to do, because the JK flip-flop is just basically hook it up to the output of the 555. How are we going to pick the values for the capacitor, the charge resistor, and the charge discharge resistor? These guys will stay the same because they're just basically there to kind of clean up the signal a little bit. They're called bypass capacitors. So what we want to do is we want to go look at the equations. And they happen to be a little lower on page 11. So we need something near 2K, 2 kilohertz. How would we go about doing that? I mean, we kind of start out with three unknowns and a bunch of equations. So how would we know what we're going to use or going to be able to do here? Some of you guys must have some ideas here. I've got a whole bunch of equations there. I got a whole bunch of variables that I don't know. I mean, if I did something like okay, I know that T high is equal to 0.693 times RA plus RB times C. And I know that T low is equal to 0.693 times RB times C. I have two equations and 5 unknowns. So are there any of those that I could start to fill in? Well, we did say that we wanted to have a 2 kilohertz frequency. How much time does one period of a 2 kilohertz cycle take? Somebody tell me how to do that. I'll bring up my grocery store calculator. How could I take 2 kilohertz and turn it into time? Dante?
Well, frequency is 1 over p, so that's 1 over p equals 2,000. So we would just
Well, 1 over 2,000 equals p.
100% equals p, yep.
Right? Yep. So I can take that and divide it by 2,000. And what does that tell me? What is that? Let me write it down over here. This is in seconds. Let me make a little s, because more properly it is lowercase s. What is that? You said it a second ago, it's the period. What is the period, Samir?
Is it a time interval?
Yeah, but of what?
Of the frequency? Like how long?
Okay, so it's how long it takes for one period or one up and down. So what do we do with that? We need to know time high and time low. And we can see just from looking at it, this number is always going to be bigger than this number. Okay, well, if this is the total time and it were 50%, what would we do to this number to see what the time high and time low were? Robert?
To me, it looks like it would be time high would be 2/3 and time low would be 1/3.
Well, we don't know that those are the same values. I mean, just reasonably thinking here, that if it were 50%, we just divide that by 2. And then this number here is time high, and this number here is time low. So that's in seconds. Equals that. It equals that. Now, we know that can't be the same because we have the b in here. But just kind of for getting us in the right ballpark, this equation here has 2 unknowns. This equation has 3 unknowns. Is there any way we can make it have 2 unknowns? Scott?
We could divide one equation by the other.
We could. Anybody else have any ideas? Not that that's a bad idea. Okay, here, look. If I were to make all of these the same, let's say I decided, okay, RA is going to be the same as RB. We know these times don't work anymore. We know that we would only have 2, but we would have a solvable equation if we could figure out what this value was. But the problem is, without just a pure guess at this point, it's going to be hard to come up with a reasonable C and a reasonable A and B, which is why the next page of this table exists, which is a chart. Now, how do you use the chart? The chart gives us reasonable answers where the values will work given a 555 timer. So we want to have 2K. Where will 2K be? Well, the values for the frequency are the lines across the screen. So if 1K is this line right here, then 2K has to be a little bit above it toward this value. Now notice that this scale is not linear, right? It's not a linear scale. From 1 to 10 and 10 to the 100 take the same amount. So there's a little log action going on here that we would have to worry about. But we know 2 is going to be somewhere near 1 and can't be too far away. One of the common things to do is to pick a value for the capacitor next. The capacitor is down here at the bottom. All these are microfarads. The closer to the center of the chart you get, the more likely it is to work favorably. And we could pick either of these 2 capacitance values. Let's pick this guy here, 0.1 microfarad. Go up until you intersect the line that's across from the 1K. And it's roughly here. As a matter of fact, that since this guy goes a little high, we'll go to where it has the next parallel line as well. Now find the thing that's labeling that particular line. So RA plus 2RB needs to equal 10K. So, well, we could pick 5K for this, 2.5K and 2.5K for this. We could pick 6666 and 3333 doubled here, right? We could pick out whatever is going to add us up to this. Now, the answers I gave you may not be correct for this value, but what you want to do is simply solve this problem. They're going to give you resistors which are in a reasonable range as long as you don't pick little 1 and 2 resistors. Will they be symmetrical? No. Why don't we care? Why don't we care that it's a not symmetrical wave coming out of our 555? Robert?
Because we're only using the 555 to toggle our flip-flop. So it doesn't really matter.
We're not using the flip-flop. We're not using the 555's clock. We're using it only to make the first flip-flop have the right value. And we know that flip-flops will square up the wave for us. So what we want to do, let's say we picked a 0.1 microfarad capacitor, and we picked here, I don't know, divide 3 into this and make one of the units there, the other 2 here. Pick that as your value for a resistor. Now you won't get exactly those, so how do we get the exact values we need? We're going to go to the resistor chart, and we're going to find a standard value that we can use for this. You then could assemble the circuit and it's going to come out close. Is it going to come out exact? No. We can trim it up. We can come up with values that are closer. We can kind of work with it. We could, by the time we have these things, we can go back to these equations, right? We can put in here now the values of the resistors we actually chose, plus the value of the capacitor, see what the time is. Oh, the time's a little short. Adjust these numbers until it's not short. Adjust this number until it's got the right value. So that's the first step when you have a complicated set of equations like this. Try to find the graphic solution and then use it to get you in the ballpark. And the closer you stay to the center of the chart, the more likely you are the values will work. Anybody have any question about that? Okay, you have a copy of this. We're going to, on Wednesday night, cover state machines, or at least begin covering state machines. Make sure you are studied up, because I'm going to start asking people who don't have their hands up. Does 2 things for me. One, it assures me that you're really sitting there and listening. And second of all, I got to get you guys some points. We're getting so close to this first exam. If you go in with a 0 in participation, you're going to have a heck of a time, doing anything on the exam that's going to, get you a passing grade. I want you to pass. I want you to understand how to do this. You're not just attending the class. Attending the class gets you a little participation, but you got to work at it. And there's some people in here that every time I ask a question, they have their hand up and they know the answer. I got to stop calling on them, because the rest of you are just trying to take a ride thinking it's somehow getting you participation points. It's not. Anybody have any questions before we are done for tonight? Okay, then I will see you guys on Wednesday evening. Be ready to work on that. And like I say, the topic is going to be state machines. There's really no prep you can do in advance, because I haven't given you the introductory slides yet. And so, review what we've done so you're in a good position to be able to talk about the material we've covered. Also, we're not that far from the exam. This will get your first studying out of the way. Don't count on just coming to a review and getting everything right. You won't. Okay, good night. Tell me good night and be gone.
Good night, Professor.
Good night.
Good night.
Good night.
Bye-bye.